Picture a universe where planets rain molten glass, where stars pack the weight of mountains into a teaspoon, and where the very fabric of space-time warps in ways that challenge our wildest imaginations. This isn't the plot of a blockbuster sci-fi film. This is the raw, unfiltered reality of our cosmos. Welcome to 49 Space Facts That Sound Fake, but are totally real, where we dive deeper into each mind-bending truth. We'll explore not just the facts, but their historical discoveries, scientific implications, and the profound questions they raise about our place in the universe. From the birth of the cosmos to the potential for alien life, fasten your seatbelt for an extended journey across the stars, filled with extra insights, expert perspectives, and cosmic wonders. Fact 1. The universe is 13.8 billion years old and still expanding. Let's kick off with the ultimate origin story. Our universe is approximately 13.8 billion years old, emerging from the explosive Big Bang. Envision a singularity, a point of infinite density smaller than an atom, suddenly erupting into a hot, dense soup of particles that cooled and expanded into the vast cosmos we know today. This age was meticulously calculated using data from the cosmic microwave background radiation, the afterglow of the Big Bang, captured by satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft. But the truly astonishing part is that the universe isn't done growing. It's expanding at an accelerating rate, with galaxies hurtling away from each other as measured by the Hubble constant, around 70 kilometers per second per megaparsec. This discovery traces back to the 1920s when Edwin Hubble observed the redshift in galactic light spectra, indicating recession velocities proportional to distance. In recent years, tensions in Hubble constant measurements from different methods, like supernovae observations versus CMB data, have sparked debates about potential new physics. Dark energy, comprising about 68% of the universe's energy budget, is the mysterious force propelling this acceleration, counteracting gravity on cosmic scales. What does this mean for humanity? In trillions of years, the expansion could lead to a big rip, tearing apart galaxies, stars, and even atoms, or a heat death, where everything fades into cold uniformity. Yet, for now, this ongoing expansion paints the universe as a dynamic, evolving entity, constantly rewriting its own story. Astronomers like Stephen Hawking once pondered if this expansion implies a finite or infinite universe, and current models suggest it's flat and potentially infinite, with no edges or center. This fact not only humbles us, but also inspires ongoing missions like the James Webb Space Telescope, JWST. Webb Space Telescope, JWST, which peers back to the universe's earliest light, revealing infant galaxies and the seeds of structure formation. Fact 2. A day on Venus is longer than its year. Venus, often called Earth's twin due to similar size and composition, harbors a temporal paradox that sounds utterly fabricated. A single day on Venus, defined by its axial rotation, lasts 243 Earth days, while its orbital year around the Sun takes only 225 Earth days. Thus, a Venusian day outlasts its year, a quirk that would make any calendar obsolete. This anomaly arises from Venus's retrograde rotation, spinning clockwise opposite to most planets, likely the result of a colossal ancient impact or gravitational torques from its thick atmosphere. The planet's dense carbon dioxide envelope, creating a runaway greenhouse effect, also exerts atmospheric tides that slow its spin further. Historical observations began with Galileo in 1610, who noted Venus's phases, but its rotation period was only accurately measured in the 1960s using Earth-based radar, revolutionizing our understanding. NASA's Magellan mission in the 1990s mapped Venus's surface in detail, revealing a world of volcanic plains and deformed terrain under crushing pressure. Temperatures soar to 460 degrees Celsius, hot enough to melt lead, and the slow rotation contributes to extreme day-night temperature variations, though the thick clouds distribute heat evenly. Scientists speculate that billions of years ago, Venus might have had oceans and a faster spin, but solar tides and atmospheric loss transformed it into this hellish world. This fact underscores planetary diversity. While Earth enjoys a 24-hour day, synced with life cycles, Venus challenges us to rethink habitability. Future missions like Veritas and Da Vinci Plus aim to probe its interior and atmosphere, potentially uncovering why it diverged from Earth's path. Imagine standing on Venus. If you could survive the pressure equivalent to 900 meters underwater, the sun would rise in the west, crawl across the sky backward, and set after what feels like an eternal day. Fact 3. A teaspoon of neutron star weighs as much as Mount Everest. Neutron stars represent the universe's extreme density champions, where the remnants of massive stars after supernova explosions compress into spheres roughly 12 miles in diameter, yet containing up to twice the sun's mass. Astonishingly, a mere teaspoon of this neutronium would weigh around 6 billion tons, comparable to the mass of Mount Everest or a billion elephants. This insane density occurs as gravity crushes protons and electrons into neutrons, forming a superfluid core possibly including exotic states like quark matter. The first neutron star was detected in 1967 by Jocelyn Bell Burnell as a pulsar, PSRB 1919+21, emitting regular radio pulses from its rapid spin. These objects rotate up to hundreds of times per second, generating magnetic fields trillions of times stronger than Earth's, which beam radiation like lighthouses. If you could approach one, the gravity would spaghettify you, stretching your body into a thin stream long before reaching the surface, smoother than a billiard ball due to immense pressure. Observations from telescopes like Chandra and Neisser have revealed glitches in their spin, hinting at starquakes cracking the crust. In binary systems, neutron stars can accrete matter, spinning up to millisecond periods, and mergers produce gravitational waves, as detected by LIGO in 2017, confirming heavy element formation like gold. This fact probes the limits of quantum mechanics and general relativity, where density approached those of atomic nuclei. Theorists like Subramanian Chandrasekhar predicted stellar collapse limits in the 1930s, laying groundwork for black hole theory. Neutron stars challenge our intuition, serving as natural laboratories for physics impossible on Earth, and their study could unlock secrets of matter under extreme conditions, perhaps even dark connections. Fact 4. Saturn's rings are a cosmic masterpiece. Saturn's magnificent rings, a hallmark of the solar system, span over 170,000 miles in diameter, but are remarkably thin, often less than 30 feet thick in places, composed primarily of water ice particles mixed with rocky debris, ranging from dust specks to house-sized boulders. These rings aren't solid but billions of orbiting fragments, likely remnants of a disintegrated moon or captured comet shredded by Saturn's gravity tides, as proposed by theories dating back to James Clerk Maxwell in 1859. Galileo first glimpsed them in 1610 as ears, but Christian Huygens identified them as rings in 1655. Modern insights from Voyager 1 and 2 in the 1980s and the Cassini orbiter from 2004 to 2017 revealed intricate structures, spokes, braids, and waves caused by moonlet interactions and electromagnetic forces. The rings are dynamic, with particles constantly colliding, coalescing, and raining onto Saturn at 10 tons per second, suggesting they're relatively young, perhaps 100 million years old, or continually replenished. Cassini's grand finale dives through the rings detected minimal dust, confirming their purity. Scientifically, they exemplify resonance phenomena, where moons like Prometheus sculpt gaps like the Cassini division. Culturally, Saturn's rings inspire awe, symbolizing cosmic beauty, and their study aids understanding of protoplanetary disks around young stars. As they slowly dissipate over millions of years, we're witnessing a transient phenomenon, a frozen snapshot of planetary evolution. Future missions might sample ring material, revealing solar system origins. Fact 5. The Sun dominates the solar system's mass. The Sun, our local star, commands an overwhelming 99.86% of the solar system's total mass, with all planets, moons, asteroids, and comets amounting to a paltry 0.14%, essentially negligible cosmic leftovers. This G-type main sequence star, with a diameter of 1.4 million kilometers, could engulf 1.3 million Earths, its gravity orchestrating the orbits of 8 planets and countless smaller bodies via Kepler's laws. Ancient civilizations revered the Sun as a god, but heliocentric models by Copernicus and Galileo shifted paradigms. Modern solar physics, advanced by spacecraft like SOHO and Parker Solar Probe, reveals a core fusing 620 million metric tons of hydrogen per second into helium, releasing energy equivalent to billions of nuclear bombs. This fusion powers Earth's climate, life, and auroras through the solar wind, a plasma stream extending to the heliopause. The Sun's mass influences everything from planetary formation, accreting from a nebular cloud 4.6 billion years ago, to its future evolution into a red giant. Discrepancies in solar neutrino counts once puzzled physicists, resolved by neutrino oscillation discovery, earning Nobel Prizes. Helioseismology studies internal waves, mapping convection zones. This dominance highlights stellar systems' typical structure, where central stars hoard mass, and underscores the Sun's role in habitability. Too massive, and it would burn out quickly. Too small, and planets might freeze. As we face climate change, understanding solar variability, like the Maunder minimum's link to little ice ages, becomes crucial. Fact 6. Glass rain on HD 189733b. Exoplanet HD 189733b, located 63 light-years away in Vulpecula, endures hellish conditions where silicate particles in its atmosphere condense into molten glass rain, hurled sideways by supersonic winds exceeding 5,400 miles per hour. This hot Jupiter, a gas giant orbiting its star every 2.2 days at a scorching 1,700 degrees Fahrenheit, was discovered in 2005 by transit photometry, dimming its star's light. Hubble Space Telescope spectra revealed its cobalt blue color from Rayleigh scattering, but the glass rain, corrosive silicate droplets, forms as vapors cool in high-altitude storms. Models suggest winds driven by extreme temperature differences between day and night sides, locked by tidal forces. Spitzer Infrared Telescope detected atmospheric escape, with the planet losing mass like a comet. This world exemplifies extreme exoplanetary weather, contrasting Earth's gentle rains, and challenges models of atmospheric chemistry. As one of the first transiting hot Jupiters studied, it paved the way for JWST's deeper analyses of exoplanet atmospheres, searching for biosignatures. Imagining life there is impossible, but it teaches us about planetary migration, how such giants end up so close to stars, and the diversity of worlds beyond our system. Fact 7. Black holes aren't cosmic vacuums. Contrary to popular myth, black holes aren't insatiable vacuums devouring everything indiscriminately. Their gravity obeys inverse square laws, allowing stable orbits at safe distances, much like planets around stars. However, beyond the event horizon, a point of no return where escape velocity exceeds light speed, nothing escapes, not even light. Predicted by Einstein's general relativity in 1915, black holes form from stellar collapse or mergers, with stellar mass types, 5 to 100 solar masses, and supermassive ones, millions to billions, at galaxy centers. The first direct image of M87's black hole by the Event Horizon Telescope in 2019 showed a fiery accretion disk silhouetted against the shadow. Hawking radiation, theorized in 1974, suggests slow evaporation via quantum effects, though unobserved. Gravitational waves from mergers, first detected by LIGO in 2015, confirm their existence and properties. Black holes warp spacetime, causing time dilation, clocks near 1 tick slower, and lens light in gravitational lensing. They play key roles in galaxy evolution, regulating star formation via feedback. This fact demystifies them, portraying black holes as natural endpoints of massive stars rather than monsters, and inspires quantum gravity quests like string theory. Fact 8. Milky Way Andromeda Collision. In approximately 4 billion years, our Milky Way will collide with the Andromeda Galaxy, currently 2.5 million light-years away and approaching at 250,000 miles per hour. This event, more a merger than destruction due to vast interstellar spaces, stars have a 1 in a million chance of colliding, will reshape both into a larger elliptical galaxy dubbed Milkomeda. Hubble data from 2012 projected this trajectory, building on earlier estimates. During the dance, gas clouds will trigger starbursts, illuminating the skies, and our sun might be flung to the galactic outskirts. This cosmic ballet exemplifies galaxy evolution, where interactions drive morphology changes, as seen in antennae galaxies. No need for alarm. Humanity, if surviving, will witness a spectacular show. Studies of local group dynamics reveal Andromeda's past mergers, hinted by stellar streams. Fact 9. Jupiter's Great Red Spot. Jupiter's Great Red Spot, a colossal anticyclonic storm persisting for at least 400 years since Giovanni Cassini's observations in 1665, spans twice Earth's diameter with winds up to 400 miles per hour. Its reddish tint arises from upwelling chemicals like ammonium hydrosulfide reacting with ultraviolet light. NASA's Juno mission, arriving in 2016, probed its depth to 200 miles, revealing roots in deep atmospheric layers. Though shrinking from 25,000 miles in the 1800s to 10,000 miles today, possibly due to diverting jets, it exemplifies gas giant meteorology, driven by internal heat and rotation. Voyager flybys in 1979 captured its turbulence, and future Europa Clipper could provide side views. This storm dwarfs Earth's hurricanes, highlighting Jupiter's role as a weather laboratory. Fact 10. The Moon is drifting away. Earth's moon is receding at 1.5 inches per year, a rate measured by Apollo-placed retroreflectors since 1969 using laser ranging. This drift results from tidal friction. Earth's rotation slows, transferring angular momentum to the moon's orbit. In 1 billion years, days will lengthen to 25 hours, and total solar eclipses will cease as the moon appears smaller. The moon's formation from a Mars-sized impact 4.5 billion years ago left it locked, always showing one face. This recession stabilizes Earth's axial tilt, moderating seasons. Fossils show ancient days were 18 hours, corroborating the trend. Future implications include weaker tides, affecting marine life. Fact 11. Space is silent. The vacuum of space lacks medium for sound waves, rendering it profoundly silent. No echoes from exploding stars or rocket roars. Astronauts hear only via bone conduction or radios. Sounds like black hole mergers are gravitational waves converted to audio. Apollo crews reported the quiet as isolating, emphasizing space's alienness. This fact aids sonification in astronomy, translating data into sound for analysis, like Chandra's X-ray sonifications. Fact 12. Mercury's odd day-year cycle. Mercury's orbital year is 88 Earth days, but its sidereal day lasts 59 days, and solar day 176, due to 3:2 spin-orbit resonance from solar tides. The Sun appears to retrograde at perihelion. Mariner 10 in 1974 confirmed this, revealing a cratered world. This resonance stabilizes Mercury against chaos, offering insights into exoplanet habitability. Fact 13. Olympus Mons, the giant volcano. Mars's Olympus Mons towers 16 miles high, covering an area like Arizona, formed by prolonged lava flows in low gravity without plate tectonics. Viking orbiters discovered it in 1971. Inactive for millions of years, residual heat suggests potential activity. Comparing to Hawaii's Mauna Kea, it highlights Mars's geological history, possibly with past water. Fact 14. The Diamond Planet. 55 Cancri, a super-Earth 40 light-years away, may have a diamond core from high carbon content and pressure, orbiting in 18 hours at 2,000 degrees Celsius. Discovered in 2004, Spitzer data suggests a lava ocean. This challenges carbon planet models, contrasting silicon-based Earth. Fact 15. The Sun's fiery core. The Sun's core, at 15 million degrees C, fuses hydrogen at rates powering all life, studied via neutrinos and helioseismology. Bohr-Exino experiment resolved neutrino flavors. The Sun's 5 billion-year future expansion threatens Earth, but current stability enables solar power tech. Fact 16. Voyager 1's interstellar voyage. Voyager 1, launched 1977, entered interstellar space in 2012, now 15 billion miles away, sending data via 23-watt transmitter. Its golden record holds Earth's greetings. As batteries fade by 2025, it symbolizes human exploration. Fact 17. Ice on the Moon. Lunar poles shadowed craters hold billions of tons of water ice, confirmed by Chandrayaan-1 and LaCrosse. Artemis program eyes it for fuel. Ice from comets or reactions. It's key for sustained presence. Fact 18. Betelgeuse, the supergiant. Betelgeuse, 700 solar diameters, could explode soon, bright as the moon. 2019 dimming from dust, not imminent supernova. Orion's shoulder. It's a variable star studied for stellar death. Fact 19. Pulsars' insane spin. Pulsars spin up to 716 Hz, conserving angular momentum from progenitor stars. Millisecond pulsars, spun up by accretion, test relativity. Crab pulsar, from 1054 supernova, powers its nebula. Fact 20. Venus's crushing atmosphere. Venus, Earth's closest planetary neighbor, is shrouded in an atmosphere so dense it exerts a surface pressure 90 times that of Earth's, equivalent to being 900 meters underwater in Earth's oceans. This crushing force would flatten a submarine like a tin can, making survival for probes like the Soviet Venera series a mere matter of minutes before succumbing to the environment. The atmosphere, composed of 96% carbon dioxide with traces of nitrogen and sulfuric acid clouds, creates a runaway greenhouse effect, trapping heat to sustain surface temperatures averaging 460 degrees Celsius, 860 degrees Fahrenheit, hotter than the surface of any other planet, including Mercury, despite being farther from the Sun. This extreme heat melts lead and drives a corrosive environment where sulfuric acid rain evaporates before reaching the ground. The atmosphere's opacity blocked early observations, but radio astronomy in the 1950s revealed its hellish conditions, and NASA's Mariner 2 in 1962 confirmed the high temperatures. The Magellan mission, 1989 to 1994, used radar to map 98% of the surface, uncovering volcanic plains, lava channels, and shield volcanoes, suggesting Venus is geologically active, possibly with recent eruptions. The thick atmosphere distributes heat evenly, minimizing day-night temperature swings despite Venus's slow 243-day rotation. Scientists hypothesize that billions of years ago, Venus may have had liquid water oceans, but solar heating and volcanic outgassing triggered a greenhouse runaway, boiling them away. This fact serves as a cautionary tale for Earth's climate, illustrating how greenhouse gases can transform a potentially habitable world into an inferno. Current theories explore Venus's atmospheric dynamics, with models suggesting superrotating winds, reaching 224 miles per hour, circulate the atmosphere 60 times faster than the planet rotates. Future missions like Veritas, Venus Emissivity, Radio Science, NSAR, Topography, and Spectroscopy, and Da Vinci Plus, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, aim to study its geology and atmospheric evolution, potentially revealing why Venus diverged so drastically from Earth. The crushing pressure also affects spacecraft design, requiring robust materials, as seen in Venera 13's 127-minute survival in 1982. Culturally, Venus's inhospitable nature contrasts with its mythological beauty, named after the goddess of love, reminding us that even celestial neighbors can harbor extreme secrets. This fact challenges our understanding of planetary atmospheres and underscores the delicate balance that makes Earth habitable. Fact 21. The universe has no center. One of the most mind-bending truths about the universe is that it has no center or edge, a concept that defies our intuitive sense of space. Unlike a physical object with boundaries, the universe is the entirety of space-time, expanding uniformly in all directions, as described by Einstein's theory of general relativity. Picture a balloon's surface. As it inflates, every point moves away from every other, with no single point as the origin. This was confirmed by Edwin Hubble's 1929 observations of galactic redshift, showing that galaxies recede proportionally to their distance, implying a homogeneous expansion. The cosmic microwave background, CMB, mapped by the Planck satellite, shows uniform temperature fluctuations across the sky, supporting the idea of isotropy, no preferred center. This fact, rooted in the 1917 cosmological models of Alexander Friedman, overturns geocentric views from ancient times, like Ptolemy's Earth-centered cosmos. The absence of a center means every observer, whether on Earth or a distant exoplanet, perceives themselves as the universe's focal point, a humbling paradox. Theoretical debates persist. Is the universe finite but unbounded, like a 3D sphere's surface, or infinite? Current data favors a flat, infinite universe, but curvature measurements remain inconclusive. The multiverse hypothesis, proposed in string theory, suggests our universe is one of many bubbles, each with its own laws, further complicating the idea of a center. Philosophically, this challenges human significance, echoing Copernicus's shift from Earth-centric models. Practically, it shapes cosmology, guiding surveys like the Dark Energy Spectroscopic Instrument, DESI, which maps galaxy distributions to study expansion. The lack of an edge also raises questions about what lies beyond. Though relativity suggests the question is meaningless, space itself is all there is. This fact invites us to rethink spatial intuition, aligning with modern physics where space-time is a dynamic, malleable fabric. Fact 22. Saturn could float. Saturn, the jewel of the solar system, has a density so low, 0.69 grams per cubic centimeter, that it could theoretically float in a cosmic ocean of water, which has a density of 1.0 g/cm superscript 3. This astonishing fact stems from Saturn's composition, primarily hydrogen, 93%, and helium, 6%, mimicking the Sun's makeup, with a dense core of metals and silicates buried deep within. This gas giant, second only to Jupiter in size, spans 116,460 kilometers in diameter, but its low density results from its gaseous envelope, which compresses less tightly than rocky planets like Earth, 5.5 g/cm superscript 3. The Cassini mission, 2004 to 2017, measured Saturn's density precisely through gravitational field studies, confirming its buoyant nature. The rings, though visually striking, contribute negligible mass, being thin layers of ice and rock. This fact highlights the diversity of planetary structures. Gas giants like Saturn differ starkly from terrestrial worlds. Historically, Saturn's low density puzzled astronomers like William Herschel, who observed it in the 1780s, but Voyager and Cassini provided clarity. The planet's internal heat, from gravitational compression and radioactive decay, drives atmospheric dynamics, creating bands and storms visible from Earth. If placed in water, Saturn's equator would flatten further due to its rapid 10.7-hour rotation, enhancing its oblate shape. Scientifically, this low density informs models of planet formation, suggesting Saturn accreted gas around a small core in the early solar system. Culturally, the idea of a floating planet captures imaginations, symbolizing the surreal nature of space. Future missions could probe Saturn's core to refine density estimates, potentially revealing exotic states like metallic hydrogen. This fact also contrasts Saturn with denser neutron stars, showing the range of cosmic density scales. Fact 23. A cosmic alcohol cloud. In the constellation Aquila, 6,500 light-years away, lies Sagittarius B2, SGR B2, a massive molecular cloud containing enough ethanol to produce 400 trillion pints of beer, an astronomical brewery beyond human reach. This cloud, a stellar nursery spanning 150 light-years, is rich in complex organic molecules, including methanol, vinyl alcohol, and ethyl formate, detected by radio telescopes like the Green Bank Telescope and ALMA, Atacama Large Millimeter/Submillimeter Array. The ethanol, formed through gas phase and grain surface chemistry, highlights the universe's capacity to create life's building blocks in star-forming regions. Discovered in the 1970s, SGR-B2's molecular inventory grew with improved spectroscopy, revealing prebiotic compounds that could seed planets during star formation. The cloud's dense core, heated by young stars, drives chemical reactions, producing molecules that emit specific radio frequencies. This fact connects cosmic chemistry to astrobiology, suggesting that organic molecules are ubiquitous, potentially delivered to Earth via comets. The sheer volume of ethanol, billions of times Earth's alcohol production, underscores the scale of molecular clouds, which collapse to form stars and planets. Culturally, the idea of a cosmic alcohol cloud sparks humor, but scientifically, it's a window into interstellar medium dynamics. ALMA's high-resolution maps show SGR-B2's structure with hot cores and outflow jets. Future studies may detect amino acids, further linking it to life's origins. This fact bridges chemistry and cosmology, showing how the universe brews complexity from simple elements. Fact 24. Mars's massive canyon. Valles Marineris, Mars's grandest feature, stretches 2,500 miles along the equator, for times longer than Earth's Grand Canyon and up to 7 miles deep, earning the title of the solar system's largest canyon. This colossal rift, visible from space, formed billions of years ago as Mars's crust stretched during volcanic activity linked to the Tharsis Bulge, home to Olympus Mons. Unlike Earth's canyons, carved by rivers, Valles Marineris resulted from tectonic cracking, possibly exacerbated by ancient water flows, as evidenced by layered sediments detected by NASA's Mars Reconnaissance Orbiter, EMBRO. Discovered by Mariner 9 in 1971, it stunned scientists with its scale, covering a quarter of Mars's circumference. The canyon's walls reveal geological history, with landslides, wind erosion, and possible glacial deposits. Embro's high-rise camera captured avalanches in action, suggesting ongoing activity. The presence of hydrated minerals like sulfates hints at past water, fueling speculation about Mars's wetter past, perhaps 3.5 billion years ago when rivers flowed. This fact informs our search for ancient Martian habitability, as liquid water is key to life. Culturally, Valles Marineris inspires visions of future exploration. Imagine hiking its rim or flying drones through its depths. Scientifically, it's a natural laboratory for studying planetary tectonics, contrasting Earth's plate-driven geology. Future missions like ESA's ExoMars may sample canyon sediments, seeking biosignatures. Its sheer size challenges Earth-centric geology, showing how Mars's low gravity and static crust allowed such extremes. Fact 25. Rogue planets drift alone. Rogue planets, untethered to any star, wander the galaxy in darkness, either ejected from their systems by gravitational interactions or formed in isolation from collapsing gas clouds. Estimates suggest billions exist in the Milky Way, ranging from Earth-sized rocky worlds to gas giants. Detected via gravitational microlensing, where their gravity bends light from distant stars. These planets, like OGLE 2016, BLG 1928, challenge traditional planet formation models requiring stellar disks. Discovered since the 2000s, their prevalence suggests many failed star systems. Some may retain atmospheres or subsurface oceans, warmed by internal radioactive decay or tidal heating if they have moons, raising possibilities of microbial life in extreme conditions. The Wide-Field Infrared Survey Telescope, WFIRST, now Roman Space Telescope, aims to catalog more, refining population estimates. Rogue planets highlight the universe's diversity, showing not all worlds orbit stars. Historically, their existence was theorized in the 1990s, but microlensing surveys like OGLE confirmed them. Culturally, they evoke lonely wanderers, inspiring sci-fi like Interstellar. Scientifically, they test core accretion versus disk instability models, and their isolation makes them ideal for studying planetary atmospheres without stellar interference. If habitable, they could host life in perpetual darkness, redefining habitability. Their discovery pushes telescope technology and statistical astronomy, with implications for galactic structure. Fact 26. Voyager 1's interstellar leap. On August 25, 2012, Voyager 1, launched in 1977, became the first human-made object to cross the heliopause, the boundary where the sun's solar wind yields to interstellar space, reaching 15 billion miles from Earth. Now over 24 billion kilometers away, it continues transmitting via a 23-watt radio, powered by a decaying radioisotope thermoelectric generator, RTG. Its crossing was marked by a sharp increase in cosmic rays and a drop in solar particles, confirmed by NASA in 2013. Carrying a golden record with Earth's sounds, images, and greetings in 55 languages, it's a cosmic ambassador for humanity. The record, curated by Carl Sagan, includes music from Bach to Chuck Berry, aiming to communicate with potential extraterrestrial finders. Voyager's instruments measure magnetic fields, plasma waves, and cosmic rays, providing the first in situ data from the interstellar medium. Its longevity, despite 1970s technology, showcases engineering prowess, but by 2025, power depletion will silence it, leaving it to drift eternally. This fact symbolizes humanity's reach, bridging science and culture. Scientifically, it informs heliospheric models, revealing the sun's influence boundary. Culturally, it's a testament to exploration, inspiring projects like Breakthrough Starshot. Future interstellar probes may follow, but Voyager 1's leap remains a historic milestone. Fact 27. Jupiter's fast day. Jupiter, the solar system's largest planet, spins so rapidly that a day lasts just 9.93 hours, the fastest among planets. This rapid rotation, measured by Voyager and Juno, flattens Jupiter into an oblate spheroid, with an equatorial diameter 7% wider than its polar one. The spin generates a magnetic field 20,000 times stronger than Earth's, trapping radiation in belts that produce auroras brighter than any on Earth. Juno's 2016 to 2025 mission mapped this magnetosphere, revealing cyclotron radiation and plasma interactions. The fast rotation drives atmospheric dynamics, creating jet streams and storms like the Great Red Spot, fueled by internal heat from gravitational compression. Historically, Galileo's 1610 observations of Jupiter's moons hinted at its rotation, later refined by ground telescopes. This fact underscores gas giant physics, where rapid spin shapes weather and magnetic environments. Scientifically, it informs exoplanet studies, as many hot Jupiters rotate similarly. Culturally, Jupiter's dynamism, named after the Roman god of thunder, evokes power. Future missions like JUICE, Jupiter Icy Moons Explorer, will study its moons, but the fast day defines Jupiter's character, a spinning titan of chaos and energy. Fact 28. Hubble's Ancient Glimpse. The Hubble Space Telescope's ultra-deep field, HUDF, captured in 2003 to 2004, reveals galaxies 13.2 billion light-years away, showing light from when the universe was just 500 million years old. This image, taken over 800 hours in a tiny sky patch, contains 10,000 galaxies, some as small as 1% of the Milky Way's size, formed during the epoch of reionization when first stars ignited. Hubble's successor, JWST, enhances this with infrared, peering even closer to the Big Bang. The HUDF, building on Edwin Hubble's 1920s galaxy surveys, shows a chaotic, star-forming cosmos, with irregular galaxies merging to form spirals and ellipticals. This fact connects us to cosmic origins, revealing the universe's evolution from a hot plasma to structured galaxies. Scientifically, it informs cosmology, with galaxy counts testing dark matter and dark energy models. Culturally, the HUDF humbles us, showing our galaxy as one among billions. Future observatories like the Nancy Grace Roman Space Telescope will expand this view, mapping cosmic expansion history. The image's beauty, often displayed in museums, bridges science and art, reminding us of our fleeting moment in cosmic time. Fact 29. Titan's methane lakes. Titan, Saturn's largest moon, is the only known body besides Earth with stable surface liquids, lakes, rivers, and seas of methane and ethane, not water. Larger than Mercury, Titan's thick nitrogen-methane atmosphere, 1.5 times Earth's pressure, supports a hydrological cycle with methane rain, revealed by the Cassini-Huygens mission, 2004 to 2017. Huygens' 2005 landing captured images of drainage channels, while Cassini's radar mapped lakes like Kraken Mare, larger than Lake Superior. Titan's cold, minus 179 degrees Celsius, surface allows methane to remain liquid, cycling like Earth's water. Discovered by Christian Huygens in 1655, Titan's organic-rich surface, with dunes and tholins, complex hydrocarbons, suggests prebiotic chemistry. This fact fuels astrobiology, as Titan's subsurface ocean may harbor life, akin to Europa's. Cassini detected seasonal changes, with lakes shrinking and refilling. The upcoming Dragonfly mission, launched 2028, will fly a drone across Titan, sampling sites for chemical analysis. Culturally, Titan's alien landscapes inspire sci-fi, like Gattaca. Scientifically, it tests models of atmospheric chemistry and planetary formation, showing how Earth-like processes occur in exotic conditions. Its methane cycle parallels Earth's water cycle, making it a natural laboratory for studying habitability beyond water-based systems. Fact 30. The ISS's daily sunrises. The International Space Station, ISS, orbiting Earth at 400 kilometers and 17,500 miles per hour, completes a revolution every 90 minutes, witnessing 16 sunrises and sunsets daily. This microgravity platform, operational since 1998, hosts astronauts from multiple nations, conducting experiments in biology, physics, and materials science. The rapid orbit, tracked by ground stations, creates a surreal experience. Astronauts see the sun rise and set every 45 minutes, as noted by crews like Chris Hadfield. The ISS's solar panels power its systems, and its orbit allows continuous Earth observation, aiding climate studies and disaster response. Microgravity affects human physiology, causing muscle atrophy and fluid shifts, studied via ultrasound and exercise regimes. The station's construction, involving 15 nations, symbolizes global cooperation, with modules like Destiny and Kibbo added over decades. Culturally, the ISS inspires dreams of space living, featured in films like Gravity. Scientifically, it tests technologies for Mars missions, like 3D printing and radiation shielding. Future plans include commercial stations post-2030, when ISS may deorbit. This fact highlights human ingenuity in sustaining a foothold in space, pushing boundaries for deep space exploration. Fact 31. Stars that sing. Stars don't produce sound in space's vacuum, but they sing through vibrations, pressure waves in their interiors, detected via astroseismology. These oscillations, caused by turbulent convection, reveal a star's age, size, and composition. The sun's vibrations, studied by SOHO, Solar and Heliospheric Observatory, show P-modes, pressure-driven, oscillating every 5 minutes, mapping its core. The Kepler mission, 2009 to 2018, analyzed thousands of stars, detecting frequencies from red giants to white dwarfs, with periods from minutes to days. For example, red giant oscillations indicate advanced age, aiding galactic archaeology. Sonification converts these vibrations into audible frequencies, creating eerie music used by researchers and artists. Discovered in the 1960s, helioseismology revolutionized solar physics, confirming fusion models. This fact bridges astronomy and acoustics, showing stars as dynamic, pulsating entities. Culturally, stellar songs inspire composers, like those at NASA's Chandra Sonification Project. Scientifically, it refines stellar evolution models, predicting lifespans and informing exoplanet searches by characterizing host stars. Future telescopes like Plato will expand astroseismic surveys, mapping Milky Way populations. Fact 32. The egg-shaped planet. WASP-12b, a hot Jupiter 870 light-years away, is stretched into an egg shape by its star's intense gravity, orbiting every 1.1 days at 2,200 degrees Celsius. Discovered in 2008 via transit photometry, its deformation results from tidal forces near the Roche lobe, where material escapes, forming a disk around the star. The Transiting Exoplanet Survey Satellite, TESS, confirmed similar distorted exoplanets. Its atmosphere, bloated by stellar heat, contains carbon monoxide and methane, detected by Hubble and Spitzer. This fact illustrates extreme tidal dynamics, unlike anything in our solar system, where planets maintain spherical shapes. Historically, hot Jupiters like WASP-12b, first found in the 1990s, upended planet formation theories. suggesting migration from outer orbits. Scientifically, it tests atmospheric escape models, as WASP-12b may evaporate in 10 million years. Culturally, its bizarre shape fuels sci-fi imagery. Future JWST observations will probe its composition, refining models of gas giant evolution under extreme conditions. This planet's fate, being consumed by its star, mirrors potential endgames for close-in exoplanets. Fact 33. The coldest place in the universe. The Boomerang Nebula, 5,000 light-years away in Centaurus, holds the record as the coldest natural place, at -272 degrees Celsius, 1 Kelvin, just above absolute zero. This pre-planetary nebula, observed by Hubble and ALMA, cools as gas expands at 164 kilometers per second, driven by a dying star ejecting its outer layers. Discovered in 1980 by the Anglo-Australian telescope, its bow-tie shape results from bipolar outflows, with a central star transitioning to a white dwarf. The rapid expansion lowers temperature via adiabatic cooling, outstripping even the cosmic microwave background's 2.7 K. This fact showcases extreme stellar evolution, where stars shed mass before collapsing. Scientifically, it informs models of mass loss in red giants, with implications for planetary nebula formation. Culturally, its frigid nature evokes the universe's harshness. ALMA's high-resolution data revealed dust grains and molecular emissions, hinting at complex chemistry. Future studies may link such nebulae to heavy element dispersal, seeding future stars and planets. The Boomerang's chill challenges our understanding of temperature limits in space. Fact 34. Astronauts' round hearts. In microgravity, astronauts' hearts become more spherical, as observed in ISS ultrasound studies since 2000. On Earth, gravity elongates the heart, but in space, fluid shifts cause it to round, increasing cardiac output temporarily, but risking orthostatic intolerance upon return. Studies by NASA's cardiovascular laboratory show 9 to 12% volume changes, reversible after months. This affects long-term spaceflight, as muscle atrophy and bone loss compound cardiovascular strain. Countermeasures like treadmill exercise and resistance training mitigate effects, but Mars missions require better solutions. Discovered during Skylab missions, 1970s. This fact informs space medicine, critical for deep space exploration. Culturally, it humanizes astronauts, showing bodily adaptations to alien environments. Scientifically, it tests fluid dynamics in zero-G, with applications to terrestrial heart disease research. Future studies on the ISS, using advanced imaging, aim to refine protocols for interplanetary travel, ensuring crew health over years-long missions. Fact 35. The Sun's red giant future. Narrator. In about 5 billion years, the Sun will exhaust its hydrogen fuel, swelling into a red giant up to 200 times its current size, likely engulfing Mercury, Venus, and possibly Earth. This phase, predicted by stellar evolution models, begins with a helium flash, fusing helium into carbon and oxygen. The Sun's outer layers will expand, cooling its surface to 3,000 K, giving it a reddish hue. Earth's oceans will boil away in 1 to 2 billion years due to increasing luminosity, rendering the planet uninhabitable. Studied via simulations and observations of stars like Betelgeuse, this fate was theorized by George Gamow in the 1940s. The Sun's eventual shedding of outer layers will form a planetary nebula, leaving a white dwarf. This fact underscores stellar life cycles, showing all stars evolve and die. Culturally, it prompts existential questions about humanity's future, spurring colonization dreams. Scientifically, it refines models of solar evolution, impacting exoplanet habitability studies. Observations of red giants like Aldebaran validate predictions. Future solar monitoring will track early signs of luminosity increase, informing long-term planetary strategies. Fact 36. Earth's cosmic cousin. Kepler, 452b, 1,400 light-years away, is a super-Earth orbiting in its star's habitable zone, where liquid water could exist. Discovered by NASA's Kepler mission in 2015, it's 60% larger than Earth, likely rocky, with a 385-day orbit around a sun-like star. Its mass, estimated at 5 Earth masses, suggests a dense atmosphere, possibly with greenhouse gases. While not confirmed habitable, it's a prime candidate for life, sparking SETI searches. The Kepler telescope's transit method detected its stars dimming, a technique revealing thousands of exoplanets. This fact fuels the search for Earth 2.0, with JWST poised to analyze its atmosphere for water vapor or methane. Historically, exoplanet discoveries since 1995 shifted astrobiology's focus, and Kepler 452b's similarity to Earth inspires hope. Culturally, it evokes dreams of interstellar migration as an avatar. Scientifically, it tests habitability models, considering stellar age, 6 billion years, and radiation. Future missions may confirm its composition, advancing our quest for life beyond Earth. Fact 37. Space smells like burnt steak. Astronauts returning from spacewalks report a distinct smell on their suits, like burnt steak, welding fumes, or gunpowder, attributed to polycyclic aromatic hydrocarbons, PAHs, formed in dying stars and nebulae. First noted during Apollo missions, this odor, detected in airlocks, arises when space-exposed materials react with oxygen. PAHs, carbon-rich molecules, are ubiquitous in the interstellar medium, detected via infrared spectroscopy by Spitzer and Sophia. This fact links cosmic chemistry to human senses, showing the universe's molecular complexity. Scientifically, PAHs are prebiotic, potentially seeding Earth via comets. Culturally, the smell humanizes space exploration, grounding the cosmic in familiar terms. EVA reports from ISS astronauts like Peggy Whitson describe it vividly. Future sample return missions may analyze these compounds, tracing their origins to supernovae or carbon stars. This quirky fact bridges sensory experience with astrophysics, showing how exploration reveals unexpected connections. Fact 38. The largest star. Scuti, a red supergiant in Scutum, is the largest known star, with a radius 1,700 times the Sun's. Replacing our Sun, it would engulf Saturn's orbit. Measured via interferometry by the Very Large Telescope, VLT, its size fluctuates due to pulsations, complicating estimates. Discovered in 1860, its variability as a semi-regular pulsating star was studied by AVSO, American Association of Variable Star Observers. At 9,500 light-years, it's nearing its end, likely exploding as a supernova within 1,000,000 years, producing heavy elements. This fact showcases stellar extremes, contrasting our Sun's modest size. Scientifically, it tests models of massive star evolution, where radiation pressure battles gravity. Culturally, Scuti's enormity inspires awe, dwarfing human scales. Future observations may refine its size, as estimates vary, 1,200 to 2,000 solar radii. Its instability, shedding mass via stellar winds, informs supernova progenitor studies, linking to element formation like oxygen and gold. Fact 39. A cosmic water reservoir. Near the quasar APM 08279 plus 5255, 12 billion light-years away, lies a water vapor cloud containing 140 trillion times Earth's ocean water, the largest known reservoir. Detected by radio telescopes like Z-SPEC in 2011, it surrounds a supermassive black hole, powered by accretion and emitting energy as a quasar. Water molecules, excited by intense radiation, emit maser signals, revealing their presence in the early universe, 1.6 billion years post-Big Bang. This fact shows water's abundance, formed via oxygen reactions in gas clouds. Scientifically, it informs early universe chemistry, suggesting water was common during galaxy formation. Culturally, it evokes wonder at cosmic scales, contrasting Earth's finite resources. The quasar's extreme environment, with temperatures exceeding 10,000 K, contrasts the cold molecular gas, highlighting diverse conditions. Future ELMA observations may map similar reservoirs, tracing water's role in star formation and galactic evolution. This discovery bridges cosmology and chemistry, showing how fundamental molecules persist across cosmic time. Fact 40. Pluto's heart-shaped glacier. Pluto's Tombaugh Regio, a heart-shaped nitrogen ice glacier larger than Texas, dominates its surface, revealed by NASA's New Horizons in 2015. Named after Pluto's discoverer, Clyde Tombaugh, this feature, spanning 1,000 miles, is part of Sputnik Planitia, a basin filled with convecting ice driven by internal heat, possibly from a subsurface ocean. The glacier's smooth, craterless surface suggests recent geological activity, reshaping Pluto's image from a static rock to a dynamic world. New Horizons flyby detected nitrogen, methane, and carbon monoxide ices, with convection cells creating a quilted pattern. This fact highlights dwarf planet activity, challenging assumptions about distant worlds. Scientifically, it informs models of icy body geology akin to Tritons. Culturally, the heart shape captured global imagination, humanizing Pluto post its 2006 demotion to dwarf planet. Future missions may probe its subsurface, seeking liquid water. The glacier's formation, possibly from an impact, underscores Pluto's complex history for 0.5 billion years in the making. Fact 41. Neutron stars' gravitational waves. Neutron star collisions produce gravitational waves, ripples in space-time, detected by LIGO and Virgo, as in the 2017 event GW 170817, which also emitted a kilonova, creating heavy elements like gold and silver. These waves, predicted by Einstein in 1916, travel at light speed, carrying information about extreme gravity. Neutron stars, with densities 10 to the power of 14 times waters, spin rapidly, amplifying wave signals during mergers. GW 170817, 130 million light-years away, confirmed multi-messenger astronomy, combining gravitational and electromagnetic observations. This fact tests general relativity under extreme conditions, refining neutron star equation of state models. Historically, LIGO's first wave detection in 2015 revolutionized astrophysics. Culturally, it underscores cosmic alchemy, producing Earth's precious metals. Future observatories like LISA will detect lower-frequency waves, mapping merger rates. Scientifically, it probes nuclear physics, as neutron star interiors may contain quark-gluon plasma. The 2017 event's gamma-ray burst linked kilonovae to short GRBs, solving a decades-old mystery. Fact 42. The first exoplanet, 51 Pegasi b, discovered in 1995 by Michel Mayor and Didier Queloz, Nobel Prize 2019, was the first confirmed exoplanet orbiting a Sun-like star 50 light-years away. This hot Jupiter, orbiting every 4.2 days, stunned astronomers as gas giants were expected far from stars. Detected via radial velocity, measuring stellar wobble from planetary gravity, it has a mass half Jupiter's and temperatures around 1,200 degrees Celsius. This discovery, using the LED spectrograph, launched the exoplanet era with over 5,000 now known. It challenged formation theories, suggesting migration via disk interactions. Culturally, it fueled dreams of alien worlds, inspiring media like Ex Machina. Scientifically, it drives exoplanet surveys like TESS, seeking Earth analogs. The planet's short orbit and high temperature make it a laboratory for atmospheric studies, with Hubble detecting sodium. Future JWST observations may reveal more, advancing our understanding of planetary systems' diversity and formation. Fact 43. Io's volcanic fury. Io, Jupiter's innermost Galilean moon, is the solar system's most volcanic body, with over 400 active volcanoes driven by tidal heating from gravitational interactions with Jupiter, Europa, and Ganymede. Eruptions, seen by Voyager 1 in 1979, spew sulfur plumes 300 kilometers high, resurfacing Io constantly. Galileo, 1995 to 2003, mapped volcanoes like Loki Patera, showing lava lakes and sulfur dioxide emissions. Tidal forces generate 100 times more heat than Earth's interior, making Io's surface a patchwork of yellow, red, and black. This fact highlights tidal dynamics, unique in our system but relevant to exoplanet moons. Culturally, Io's fiery nature evokes mythic hellscapes. Scientifically, it tests geophysical models, with implications for habitable moons like Europa. Future missions may study its magnetic interactions with Jupiter's field. Io's activity, discovered unexpectedly, shows how gravity shapes small worlds, creating extreme environment. Fact 44. Big Bang's echo. The cosmic microwave background, CMB, a 2.725 K glow from the Big Bang, fills the universe, detected by Arno Penzias and Robert Wilson in 1965 at Bell Labs. This blackbody radiation, mapped by COBE, WMAP, and Planck, dates to 380,000 years post-Big Bang, when atoms formed, freeing photons. Its tiny temperature fluctuations, 1 part in 100,000, seed to galaxies, as seen in Planck's 2013 map. This fact anchors cosmology, confirming the Big Bang and constraining dark matter/energy. Culturally, it's a snapshot of cosmic infancy, inspiring awe. Scientifically, it tests inflationary models, predicting universe flatness. BICEP experiments seek primordial gravitational waves in CMB polarization. Future observatories like Simon's Observatory will refine measurements, probing early universe physics and potential multiverse signatures. Fact 45. Supermassive black holes. Supermassive black holes, with masses from millions to billions of solar masses, reside at galaxy centers, like Sagittarius A** in the Milky Way, for million solar masses. Detected via stellar orbits and gas dynamics, they grow through accretion and mergers, powering quasars in the early universe. The Event Horizon Telescope's 2022 image of SGR A** confirmed its size. These giants regulate galaxy formation, with jets and feedback limiting star birth. Discovered in the 1960s via quasar spectra, they're central to cosmology. Culturally, they're cosmic titans, shaping sci-fi like Interstellar. Scientifically, they test relativity, with orbits revealing space-time curvature. Future LISA will detect merger waves, tracing galaxy evolution. Their formation, seed black holes or direct collapse, remains a mystery, driving research. Fact 46. Enceladus's geysers. Enceladus, Saturn's icy moon, ejects water geysers from its subsurface ocean through South Pole fractures, discovered by Cassini in 2005. These plumes, rich in salts and organics, feed Saturn's E-ring and suggest hydrothermal activity, making Enceladus a prime astrobiology target. The ocean, 10 kilometers deep under 20 kilometers of ice, is warmed by tidal heating. Cassini's Flithroughs detected ammonia and methane, hinting at life-friendly chemistry. This fact redefines icy moons as habitable prospects, akin to Europa. Culturally, it sparks visions of alien oceans. Scientifically, it tests ocean world models, with implications for exomoons. The proposed Enceladus Life-Finder mission could sample plumes for biosignatures. Its discovery shifted focus from gas giants to moons in habitability searches. Fact 47. Hypernovae outshine galaxies. Hypernovae, explosions of stars over 100 solar masses, can outshine entire galaxies, producing long gamma-ray bursts, GRBs. Detected by Swift and Fermi satellites, they result from pulsars, stars collapsing into black holes with relativistic jets. The 1998 GRB 980425 linked hypernovae to type IC supernovae, confirming their role in heavy element production. This fact showcases stellar death's violence, shaping cosmic chemistry. Culturally, it evokes cataclysmic awe. Scientifically, it tests core collapse models, with GRBs tracing early star formation. Future observatories like Theseus will map GRB populations, refining cosmology. Hypernovae's brief brilliance, seconds to minutes, contrasts their lasting impact, seeding galaxies with metals. Fact 48. Dark matter's mystery. Dark matter, comprising 27% of the universe's mass energy, is invisible, detectable only via gravitational effects, like galaxy rotation curves showing unexpected speeds. First proposed by Fritz Zwicky in 1933 for galaxy clusters, it shapes cosmic structure, forming halos around galaxies. Candidates include WIMPs, weakly interacting massive particles, or axions, but direct detection experiments like Xenon 1T have found none. The Bullet Cluster's 2006 collision showed dark matter separating from normal matter. This fact drives particle physics, seeking new fundamental particles. Culturally, it's a cosmic enigma, inspiring mystery. Scientifically, it constrains cosmological models, with Euclid mapping its distribution. Its nature, cold, warm, or self-interacting, remains elusive, potentially revolutionizing physics if identified. Fact 49. Life beyond Earth. With an estimated 2 trillion galaxies, each hosting billions of planets, the odds of extraterrestrial life seem high. The Drake equation, formulated in 1961, estimates communicative civilizations, factoring star formation, planet prevalence, and life's emergence. Exoplanets like Kepler 452b and TRAPPIST-1's worlds, inhabitable zones, fuel optimism. SETI's radio searches, like the Allen Telescope Array, and biosignature hunts via JWST target methane or oxygen. The Fermi paradox, why haven't we found aliens, suggests filters like extinction or technological limits. Discoveries of extremophiles on Earth expand life's possible forms. This fact ignites imagination, driving sci-fi and science. Culturally, it raises questions of humanity's uniqueness. Scientifically, it pushes astrobiology, with missions like Europa Clipper seeking subsurface life. Future breakthroughs may confirm microbes or signals, redefining our cosmic role. These 49 facts, now richly expanded, unveil a universe where the impossible is reality. From Venus's crushing skies to the hope of alien life, each truth deepens our awe and curiosity. As we push technological frontiers, from JWST to interstellar probes, the cosmos awaits with more secrets. Keep gazing upward. The universe's story is ours to write.